Let P2R be the vector space of polynomial in x degree at most 2 with real coefficients and M2R with a vector space of 2 by 2 real matrices. If a linear transformation T defined from P2R to M2R is by this relation, then we have to tell about T is 1 1, not on 2, not 1 1, and range space of T can be generated by this spanning set, and null space of T can be generated or spanned by this set. This is a very important question because a linear transformation, 3 or 4 types question almost which are asked in exam, either 1 1 on 2, range space of T, null space of T. It means we have to indirectly, I can explain you how to find basis, how to find a range, null space of T, and how to tell about 1 1 and on 2 for a linear transformation. So it is very good question, and I will explain you each point from bottom up to solve this question. As T is defined as a linear transformation P2 R2 M2R. First understand what is the notation. P2R is for polynomial, P for polynomial, and this tell you degree or higher degree of the variable or higher degree of the polynomial, and this is tell you coefficient of polynomial is coming from is coming from. Similarly, this is the size of matrix or square matrices, and R stand for elements of matrices are coming from. This is notation how to write a vector space in a compact form. Now T is a linear transformation. So by the property of a linear transformation, TCU plus V will satisfy CTU plus CV, and it is important field of domain and codomain must be same, otherwise this property will not hold and we cannot define linear transformation. P2R is domain here and M2R is codomain here. So first write linear transformation T in a matrix notation. So we need basis of domain and codomain. So I call basis for domain is beta 1 and basis for domain is beta 2, and this is basis 1x x square, and this is 1001, sorry 0, this is the set 0100 0010, standard ordered basis of M2R 0001, because we can write if a 2 by 2 2 by 2 matrix ABCD, if these are element, then these are linear combination of A times this one plus B times this one plus C times this one plus D times this one. So these are basis element of M2R. Now to write linear transformation in matrix notation, we will find all images of basis, all images all image of beta 1 and write them will write them in linear combination of beta 2. It means that is each element of, because of basis, each element of domain can be written as linear combination of beta 1, and each element of range of T can be written as linear combination of beta 2. So it is sufficient to find image of beta 1, elements of beta 1, and it write it in linear combination of beta 2. So we will find T1, Tx and Tx is square, because beta 1 is a 1x and x is square, and we will write them in linear combination of beta 2. We will write all these in linear combination of beta 1. First I'm going to find T1. So T1 is f is 1 here, because this is f1, and T send f as f0, f2, 0, 0, this is f1. So we need to find f0, f2 and f1. So this is constant function. So f0 is 0, f1 is, sorry, f0 is 1, f1 is also 1, and f2 is also 1. So difference is 0, 0, 0, 1, and this can be written as 0 times e1 if elements of basis 2, basis beta 2 can be represented, or say e1, e2, e3, then 0 times e1 plus 0 times e2 plus 0 times e3 plus 1 times e4. Now these coefficients 0, 0, 0, 1 will be the first column of T, or T beta 1 to beta 2. Now find Tx, which is equal to, we will find, and we'll write in linear combination of beta 2. So fx is x here, you can see fx equal to x. So f0 equal to 0, f1 is 1, and f2 is 2. So T will send x as minus 2001, and it can be written as linear combination of 0 times e1 plus, sorry, minus 2 times e1, 0 times e2 plus 0 times e3 plus 1 times e4. So these coefficients will be second column of matrix representation, and t x square we will find tx square. So tx square, here fx equal to x square. So for this f0 equal to 0, f1 is 1, and f2 is equal to 4. So fx square will be minus 4001, and this can be written as minus 4 times e1 plus 0 times e2 plus 0 times e3 plus 1 times e4. So matrix representation of T beta 1 to beta 2 is first coefficient of linear combination of beta 2 is 0 0 0 1 0 0 0 1, and second was minus 2 0 0 1, and third was minus 4. You can see here minus 4 0 0 1, minus 4 0 0 1. This is matrix representation of T and of this size 4 by 3. This is T1, this is T2, sorry, Tx, and this is Tx square. It means this is the linear combination of T1, it is linear combination of Tx, and this is linear combination of beta 2. T linear coefficients of linear combination of beta 2 for x square. Range of T will be less than equal to min of this size, min of this size, it means 4 3, so it will less than equal to 3. Now you can check number of non-zero number of non-zero rows is 2, so rank of T is 2, and by rank nullity theorem this equal to dimension of domain, and this is equal to, if P2R is given, then its dimension is 3, so nullity is 1. Nullity is 1, this implies T is not 1 1, not 1 1. If nullity is 0, then T may be, or T will be 1 1. So as in options, T is 1 1, option A is discarded here. Now we will check option B. In option B, T is onto, and in option C, range space and spanning set and null space, and it is span of this set or not. Now come to the point onto. For onto, we all know that each image of T must have pre-image, If this condition is true, then we can say T is onto, that is indirectly each image means linear combination of columns of T, because images are linear combination of this matrix. So all linear combination of columns of T should have pre-image, should have pre-image. Pre-image indirectly. Pre-image means should exist a domain element, and domain element is linear combination of 1x and x square. It means linear combination of rows of T, linear combination of rows of T, because this is telling so for onto it is necessary each row must have pivot element, and in previous slide you can see here only two rows have pivot element, so this is not onto, so this is this linear transformation not onto. This linear transformation LT is not onto. It means option B discard here. Now come to the option C, which is about range. How to find range? We already find range because matrix transformation is described about the range. And range, he is asking, range is spanning set of some elements. So we will discuss about span for range. Span also in matrix representation, we have seen L1, sorry, T1, Tx and Tx square, which are column vectors in matrix representation, are linearly independent column vector. Linearly independent column vector. So number of linearly independent column vectors is equal to number of columns in matrix. It means image, or each image is a linear combination of these Li vector. Each image is linear combination of these linearly independent column vectors. It means if we are interested to find or want to find basis for RT, it is clear that because number of linearly independent columns in matrix representation are 3, so cardinality of basis is less than equal to 3, and rank of T is showing that this basis has exactly two elements. And in option C, range of T is spanning of two elements, so it may be true. So we will check this confidently. As T1, Tx and Tx square, T1 was 0001, Tx was -2001, and Tx square is -4001. And this matrix can be written as minus 2 times or 2 times -2001 plus 0001. Here you will got 2, right here 0, right, make 0 here, so 0, and from 1 here, so finally you will get 1 here. So these are only image, and each image, this is nothing but E1, and this is another format, and this is linear combination of this one and this one. So range of T is spanning of -2001 and 0001, So option C is right here. Now come to the option D, which is about null space of T. Null space of T, and it is given that null space of T is a span of x square minus 2x comma 1 minus x. So we will find null space for T by the property of null space. If any element in domain is domain element, then this domain element T will send this domain element to 0. So if a naught plus a1 x plus a2 x square is domain element in domain, then T of a naught plus a1 x plus a2 x square equal to 0. Now consider this is a function f or polynomial x, px you can say more precisely, or fx. So fx is a naught plus a1 x plus a2 x square. Now we need to find f1, f2 and f0, 0, 1, 2 to write or got a matrix for this. F0 minus f2, here 0, 0, and this is f1. So find image of at 1. So it will be f1 is a naught plus a1 plus a2, f0 is equal to a2 a naught, and f2 is equal to a naught plus 2 times a1 plus 4 times a2. So matrix format for this arbitrary element of domain is f0 minus f2, 0 and 0. f1 can be written as minus 2 times a1 minus 4 times a2, 0, 0, and this is a naught a1 plus a2. And by the property of null space, T elements of domain should be 0. So it is equivalent to 0 matrix. From equality of two matrices, minus 2 times a1 minus 4 times a2 equal to 0. This implies minus a1 minus a1 minus a2 equal to 0, minus 2 times a2. So a1 equal to minus 2 times a2, and this fourth entry or a22 entry is showing that a naught plus a1 plus a2 is equal to 0. So a2 is free variable here. So it can be written as a1 equal to minus a1 minus of a2, and a1 is, so it will be minus of a1 minus of a1, it means 2 times a2 minus a2, this is a2. So a1 is equal to a2. You can check if there is some calculation mistake. So any element of domain or elements which are in null space can be written as a1 is a2 and a naught, this is a naught, and a1 is minus of 2 times e2x, and e2 is, this is e2, and e2 is free variable here. So this is a naught plus a2 minus 2 times x plus x square. So null space, this is linear combination of this set. So null space of T is not a spanning set of x square minus 2x comma 1 minus x. So this option was wrong. So only correct option is option C. So in this question, because defining of this question was very important, and I explained you each point, either one on two, how to find null space, range space, and basis of these. It means in compact format, or in a short time, you can find easily. If this question is asked in MCQ format, then you can easily, or speed, in speed, you can tell about the correct option.